Normal distribution table, type 2, finding z. So what's important to note here when we're looking for our z value in these questions is that we're going to be given the probability. And if we're given the probability greater than 0.5, then we know that the z-score is going to be a positive value. Whereas if we're given the the probability less than 0.5, then we know the z-score has to be a negative value. Because if we sketch our normal distribution curve, here we have 0. So of course everything here is going to be at 0 will be 50%, okay? So less than, so a value over here would be a negative z-score. Anything over here would be a positive z-score. So therefore, say in the first one here, we have the probability of z less than or equal to a is equal to 0.7324. So what that means then is that 73% of the graph is shaded in, which means clearly we are in a positive region. Whereas for the second one, we have the probability that z is less than or equal to a is only 17% of the graph. So it's a very small area. So in other words, it's less than 0.5. So at this point here, all of that is 0.5. So if we're less than 0.5, we're in the negative zone. Okay, so therefore we're going to have to work out our values and then apply this 1 minus p of z less than or equal to k. Okay, so let's have a look at how we're going to do that. So we're going to go with first one, where we have the probability that z less than or equal to a is equal to 0.7324. So again, we sketched our graph every time, and we say this is the z-score that we're looking for. So in this case they're calling it a. So we're looking for the value of a, given that all of this is 0.7324. Okay, so to do that we have to go to our tables, and rather than looking at the z-score down the side, what we're going to have to do is try and actually find the probability. So 0.7324, so 7324, so there it is there. Okay, so that means if I go across, I have 0.6, and if I go up, I have 0.02. So therefore, A must be equal to the z-score 0.62. Okay. So for the second one, we have to find the probability that z is less than or equal to a, given that that probability is 0.1724. So again, I know that that's going to be a negative value because the probability is less than 0.5. So in other words, that's a there. So that probability is 0.1724. So basically, I know with my symmetry that if I get this value over here, a, then those two shaded regions will be exactly the same. And of course, then if I take 1 away from all of this red bit, so 1 minus the probability that z is less than or equal to a, well then that will give me the blue region, which is equal to the red region. Okay, so therefore, if I go 1 minus 0.1724, which is the probability, then that will give me a value of 0.8276. And now if I go to my tables, let me rub out the last one. Well, now I can see, well, my tables start, remember, at 0.5. Okay, hence I couldn't find 0.1724 on them. So now I can see where is 0.8276. So we can see in this case we don't actually have 0.8276 in our tables, and this often happens. So we have to make a judgment call. So we have 0.8264 and 0.8289. Okay, so therefore our value 0.8276 lies somewhere between these two values. So in other words, it lies somewhere between 0.894 and 0.895. And we have to see, well, which value is it closer to? If it's exactly halfway between the two, this is really important to note. If it's exactly halfway between the two, so it is equally close to 0.94 and equally close to 0.995, then what we would have to give as our answer would be 0.945. Okay, in other words, exactly halfway. But in this case, we can actually see it's 0.0012 away from 0.64, and it's 0.0013 away from 0.829. So it's actually closer to the 4 side, in which case we would say, therefore, that A is equal to 0.94. Now, again, we have to note that it can't be 0.94 because that represents this value here. That's 0.94 for our z-score. We're on the negative side. So we say, but A is negative, because remember at the start the probability was 0.1724, and therefore we say, hence A is equal to minus 0.94. Okay, so you're always going with the closest z-score. If it's halfway between, so if the probability lies halfway between two different z-scores, then you go exactly halfway between them. Okay, so the next one then is where we're given our range of values. So I'm going to go on to the next page for this. Okay, so just making that note there, obviously about exactly halfway or taking closest value. And if we're moving on to the next one, then we're looking for the probability that the is 0.6368, and what would be the z-scores that would give this probability. So again, we're going to start by sketching our graph. So we're going to have A and minus A, and the area between those two is represented by 0.6368. In other words, 63.68 of the graph is covered for this range, and therefore that's equal to these two graphs separated out. In other words, if we draw our normal distribution for A, then that would represent all of that area there. And then if I do minus A, well, that would be all of that area there. So in other words, the probability that minus A is less than Z, which is less than A, can be broken down into the probability that Z is less than A minus the probability that Z is less than minus A. But of course, the probability that Z is less than minus A is the same as saying 1 minus the probability that Z is less than or equal to A, because of that symmetry. So of course, if I get rid of the brackets there, I'll have minus 1, and then I'll have minus the probability that Z is less than or equal to A, which is the same as the probability that Z is less than A. So I end up with two of those, minus 1. And as I said earlier, the less than and the less than or equal to, there's no difference between them because it's minimal differences. It's negligibly small. Okay. So therefore, this must be equal to the probability that I was given at the start, which is 0.6368. So what we want to do then is try and get the probability that Z is less than A on its own. So if I bring 1 over to the right hand side, I'm going to get 1 plus 0.6368. And then if I divide across by 2, I'm now left with something that I can work with. So dividing across by 2 gives me 0.8184. And now this goes back to, if I go back to the previous page, it goes back to the very first example there. It's exactly the same. Okay. So all we need to do now is try and find 0.8184 in our tables. So if we go up to our table, and if I erase the last ones, so we're looking for 0.8184. So again, 0.8184. Well, I don't have 0.8184, but what I do have, if I highlight that better, is 0.8186. Now I can see that it must be 0.8186 because the next value just underneath it is 0.8159, which is much further away. Okay, so therefore the value, if I go across, has to be 0.9, and if I go up, has to be 1. So in other words, A has to be 0.91. So in other words, the probability of minus 0.91 less than Z less than 0.91 would give me a value of 0.6368. Okay, so we're going with the closest value. So the 0.8186 is closest to 0.8184. Okay, so what I'll get you to do is have a look at the next example, and you're going to put a big fat NB next to this example. This is really, really important, okay, because this is going to come up at a later stage when we're doing statistics 3 and we're doing hypothesis testing. But this is a nice, interesting question. So the question reads, if 95% of a normally distributed population lies within X standard deviations of the mean, what is the value of X? So first thing we always do with these questions is sketch our graph. So there's our mean, and we're told that the population lies within X deviations of the mean. So this would be X plus the mean and X minus the mean. And we want to know what is the value of X. So that would be X plus the mean, and this would be X minus the mean. Okay, so we want to find the value of X. Now, if we actually work this out perfectly, well, what we have then is the probability that Z, that minus X lies between Z, which lies between X, and equals 95% would be 0.95. So what we have to do then is actually, again, separate out this graph. So like in the previous case there, we saw that that can be written as the probability that Z is less than or equal to X minus 1 minus the probability that Z was less than or equal to X. And in other words, that becomes 2 times the probability that Z is less than or equal to X minus 1. And if I bring 1 to both sides, we end up at 1.95. And then if I divide 1.95 by 2, we end up with 0.975. So let's go back to our probability tables. I'll remove the last one. And we look for 0.975. And 0.975 is an exact figure here in our tables. And what that actually reads off for us is 1.9 and up 1.96. So therefore, the value here for X is 1.96. So in other words, when we're looking at 95% of the normally distributed population, what we're actually looking at is the mean plus or minus 1.96 deviations away from the mean. And this is really, really important because this is known as our critical values. And of course, if we go back to the empirical rule, normally we would say that 95% is lying within 2 deviations away. So normally we would say that's actually 2 deviations and minus 2 deviations away from the mean. And therefore that gives us a value of 95% based on our empirical rule. So of course 1.96 deviations away rounds to 2, but the exact value is 1.96. And this is essential for our hypothesis testing when we're looking at 95% confidence intervals at a later stage.